Good morning to one and all everyone present here. So today's session we will be discussing on a topic called as data path architecture. So before running through this topic, I would like to discuss in detail between a connection between memory and processor. Okay. As we know, memory is arranged in a form of an array, and each box is called as cell. And each cell can hold one bit of information. That is, this cell can hold one bit, this cell can hold one bit, this cell can hold one bit, and it goes on. If you have a memory of 64 KB, you will be having 65,535 cells. Storing one bit and retrieving one bit becomes a tedious process. So what we do is, we arrange 8 bits to form as one word. We can also arrange 16 bits to form one word. We can also arrange 32 bits to form one word. Like that, we can also arrange 64 bits and 128 bits form one word respectively. Okay, but always one byte is of 8 bits. So the byte remains constant and the word changes. So you have on the other side processor. As we know, processor has various registers. One of the registers is called as MAR. Second one is MDR. It also has an IR. We will be discussing all these things in detail with the help of an example. And the next one is program counter. Then you have different registers R1, R2, then Rn-1. Then you have control unit and your ALU. MAR is connected to a memory with the help of memory address lines, and it's a unidirectional. MDR is connected to the memory with the help of MDR, memory data lines, but it's a bidirectional. And the same way, control unit is connected to the memory with the help of a control bus, which is also bidirectional. Consider you have some instruction saying add of A comma B. You have some other instruction subtract of X comma Y. Each cell is having a unique address. So consider this address is 232. Another address is 233. Your processor wants the address 232 to be fetched from the memory. So you have the program counter will be having 232 initially. This particular address will be given to MAR. So as of now, MAR will be having the address number 232. This address 232 will be sent to the memory with the help of memory address lines. Simultaneously, the program counter will be incremented so that it will be pointing towards the next instruction to be fetched. So the role of the program counter is to fetch the next associated instruction. It holds the address of the next instruction to be fetched. As of now, it has given 232. The memory address register is holding the address of the instruction to be fetched. The address will be traveling with the help of an address lines on the address bus. The memory will fetch the address, go to that particular address, fetch the instruction and place the instruction, that is the data, on the data lines, that is add of A comma B, and the data will be available in the memory data. After MDR, the instruction will be given to IR. The instruction will be given to IR. So instruction register is the place where the currently executed instruction is residing. Program counter holds the address of the next instruction to be fetched. Memory address register holds the address of the executing instruction, and memory data register tells a read or write operation has to be performed. In this case, what are we doing? A read operation on the memory. The control unit will generate the appropriate signals. So keeping this in mind, we will go ahead and build up a typical data path architecture. The word typical means nothing special about it. Okay? So before getting inside the data path architecture, data path. So what do you mean by that? How the data is moved from one place to another on the processor side. How the data is moved from one place to another on the processor side, and who is controlling the data for the movement. Who decides which path it has to take will be done by the controller. So before getting inside it, you have various components of a data architecture. The first one we will be seeing is ALU. As we know, ALU stands for arithmetic and logical unit, which does addition, subtraction, multiplication, division, OR, AND, XOR, and various different arithmetic and logical operations. The second one we will be seeing is register. Registers are the one which stores the data on the processor side. Registers are the one which stores the data on the processor side. The next one we will be seeing is the multiplexer. I am introducing a new term which is otherwise called as mask. So first we will discuss about multiplexer, then we will come back to A. The term multiplexer means multiple inputs, that is input 1, input 2, input 3, input n, and one output. Yes, multiple inputs and one output. Now the output will be selected from the couple of given inputs. So who will be selecting the output from the given couple of inputs is the controller. So the controller decides which input to be selected and given as the output. Suppose say if I have a 2-bit input multiplexer. So my diagram will look like this. Input A, input B. It will either select A or else B. So 1 is going to be the output. So because there are just 2 inputs, one control signal line is enough to select A or else B. Is this clear? This is called as. So it just selects either A or B and transfers only one at a given time. One is going to be the output. The next one we will be seeing is ALU, arithmetic and logical unit. So as we know, ALU is used to perform different ALU operations. Consider you have a system, you have an logical operations. So in total we have 32 different functional operations. Yes? To represent 32 different functional operations, how many bits are required? We require 2 to the power of 5 bits, that is 32, to represent a unique operation code. Yes? We require 5 bits to represent. If add, we require a separate code. For subtract, we require a separate code. Like that, for 32 different operations, if we require a separate code, we require 5 bits. Consider we have an ALU. Input A, input B. In terms, we can also write it as A leg, B leg, and 1 output. So now, A leg, B leg, so here ALU can perform 32 different operations. So we require 5 bits. So consider we have 5 bits. We call it as C0, C1, C2, C3, C4. If you are doing an addition operation, so you will be having a code something like 00101 arbitrary I am assigned. So if you are doing a subtraction operation, you will be having a code 01001 arbitrary I am assigned. There will also be a code for XOR operation 00111. There can also be a code for division operation 1111 something. It can perform arithmetic operation and logical operation. It can also perform, or it can also do the operation of a multiplexer. It can just take the value of A and pass it, or the value of B and just pass it. So there will be a output code if you are just passing the value of A without performing, you are not performing anything, just taking the value of A and passing as it is. You will be having a code for, say for example 001011. It's already there. So we will have it as 10. So if 10100 means it will just take the value of A and pass it. It will not do any ALU operation. There will also be a code for B out 11101. So if this code is selected, arbitrarily I am assigning, it will just take the value of B and pass it. It will not do any ALU operation. And we also have the third component called as a register. As we know, the register are the place where just stores the data on the ALU side, on the processor side. So keeping all these components, ALU, register and multiplexer, we will build up a typical data path architecture. As we know that ALU is the core or the heart of the processor, we will start with ALU. And 1 output. So you have A input, B input and 1 output. You have different registers. If you look at this diagram, we will be talking about this particular structure alone. We will not include this part. But as we know, we will be considering this diagrammatic part alone. So you have address lines going to the memory, which is connected to the help of address bus. and the data lines. And on the other side we have memory. We will not be discussing that over here in detail. So we have different registers. The first one is your instruction register. The second one we have memory address register, which holds the address of the currently executed instruction. While talking about instruction register, it holds the instruction itself, currently executing instruction itself. The next one we will be talking about, consider you have two data. So D1 register, data 1 register, memory data 1 register, data 2 register. Then you have the program counter. We are talking about program counter. The definition of the program counter is it holds the address of the next instruction to be executed. The program counter is a place which decides which instruction to be executed next. So consider we have one of the input is connected to one of the ALUs. Another input can either come from data to register or a program counter. We can just pass the data or else the contents of the program counter. So we have a multiplexer connected over here. And either data register or the contents of the PC will be transferred to the ALU operation. So depending on that, again we'll add another mux over here. Right? So if you see this particular diagram, if the arrow mark is like this, I am talking about memory data register. It's a bidirectional. If the arrow mark, that is, if the data is going from the processor to the memory, we are going to do a write operation of the memory. If the data is coming from the memory to the processor, we are going to do a read operation from the memory or on the memory. Clear? So in general, we are giving this particular thing as a bidirectional. So either a read operation can be done on the memory or a write operation can be done on the memory. So if you see this is the data bus, which is otherwise called as the D bus. If we are going to do a read operation on the memory, the data has to come from the memory. So the data will come from the memory. Clear? If we are going to do a write operation on the memory, the data has to go out from the processor to the memory. Yes? I repeat, either you can do two operations, a read operation or a write operation. If you are going to do a read operation on the memory, the data will come from the memory, that is from the processor to the memory. If you are going, that is from the memory to the processor. That's a read operation. If you are going to do a write operation, the data will go from the processor to the memory. So that is what has been explained. So if it's a read operation, the data is coming inside the processor. If it's a write operation, the data is going out of the processor to the memory. On the other side, we have the memory. Yes? And what is the next step we have to do? First step, at the time t1, if you want to fetch any instruction, the contents of the program counter has to be placed into MAR. The contents of the program counter has to be placed into MAR if you want to fetch the instruction add of A, B. Yes? So, as of now, the contents is 232. This particular 232 has to be placed in MAR. So the contents is here. The data, the multiplexer can select either D2 register or the contents of the program counter. The first step is to place the contents of the program counter into MAR. Yes? So how the data path is going to be? So the contents of the program counter is selected. So either from D2 register or PC, which is selected, the multiplexer is selecting the contents of the program counter. And again, it can select the contents of the D1 or the max. It is selecting the B line because the contents of the B program counter is in the B line, and it is giving to the process. That is, it is giving to the, you have another marks over here. It can either the data is coming from the memory or else it is going out. So here the data is going out. So we need to draw the contents. As of now, it is selecting the multiplexer, is selecting this line. So after that, it has to be given to the MAR. So I am connecting, I am making things complicated here. So yes. So if you see at time t1, the contents of the program counter should be placed into MAR. Yes. So this path is being selected. The first step is to select MAR. PC is given to multiplexer. The multiplexer is selecting either from D2 or PC, contents of PC. This line is being selected. That is 232. This is the contents where the instruction is. Yes. Now after that, there is some other data D1 is there and the contents. So because it's selecting, so 232 is here. So again the multiplexer is selecting transfer. That's it. So after that, the data 232 is passed on to the thing and 232 is being passed on. Yes, and it is given to the MAR. Okay, as of now, MAR has which address to be fetched from the memory. The address to be fetched from the memory. Okay, and the data is going out. So you have the address bus over here. So the data is going out. So we can't, I am not going to explain you what is on the other side. That is, the data is what? This is the address bus. This is the data bus. And this is the control bus. So at time t1, the contents of the program counter is placed into the MAR. So the data path for placing the contents of the PC to MAR is PC. Out of 2, the multiplexer is selecting this code and it is placing. Again from A and B, it is selecting this path. It is selecting. So the multiplexer is placing 232. It is going and it is being placed into MAR. Yes. Now the data has been added. Simultaneously at time t2 in the next consecutive clock cycle. So what have you done on this? A read operation on the memory. So the control sequence is that a read operation has been done. Simultaneously, the program counter will be incremented by +1 and it will be stored in the program. That is 233 will be stored. So as of now, if you see this particular program counter at time t2, it will be incremented and 233 will be stored. So now we will be not talking about the next continuous clock cycle. So this will happen. What is happening here? A read operation on the memory. Simultaneously, the program counter will be incremented. In this data path architecture, I can't show the step T2. That's not possible. So at time T3, what is happening? The data, the memory is responding and placing the data on the data bus. So at time T3, it is fetching the instruction, and this instruction is fetched and the data is being placed on the data bus. That is, from memory to the bus, the operation is happening. At time T3, the memory is placing the data on the D bus. At time T3. At time T4, now the data is available over here. The data is given to the instruction register. So at time T4, the data from the data bus is given to instruction register. So instruction register as of now has the particular instruction, that is add of A, comma. So we will draw a data. Now, if you see this, we will call it, because there are two multiplexers, we will give a name to it. We will give a name called as MUXSA, something like this, and we will give a name MUXLP. Just to identify or differentiate between two multiplexers. So, we will have one control line bit. Because there are only two inputs, A, B. If A is selected, we will put it as 0. If the bit is 0, then the data from A is selected. Otherwise, if the input is 1, the data from the line B is selected. The same way, ELU has 32 different operations. To differentiate, to write 32 different unique code, how many bits are required? 32 bits are, 5 bits are required to represent 32. So we will have it as C0, C1, C2, C3 and C. That is, for add, if the ALU performs, add as we told before, the code will be something like this. For subtract, the code is going to be something like this. For division, the code is going to be something like this. 1, 1, 1. If you don't want to perform any addition, subtraction or any logical operation, if you just want to transfer the data of A and pass it on to the output, or B to pass it on to the output, we also have a code for that. There should be a code. Consider the code is 00001. If the code is 00001, the data from A will be passed on to the output without performing any operation. If the code is 00011, because 11 is here, we will have it as 101. The code from the data from the B will be just be transferred to the output without performing any ALU operation. And while talking about ALU, in the multiplexer, we are not bothered about how many data bits it can hold. But in an ALU, you can do a 4-bit addition, 8-bit addition, 16-bit addition, 32-bit addition, and it goes on. So if it's a 4-bit, the output is going to be 5-bit. If you are performing an addition of two numbers, which is 4-bit and 4-bit, there is a possibility that you might end up with a carry. But we are not bothered about carry. Okay? So the data has to be how many bits it is going to hold. We should specify the data when you are talking about the ALU. When you are talking about the ALU. So multiplex SA SA, if it is 0, then the data from D2 register will be selected. If the mux SA is 1, the data from the B line is selected. And you have a finite code which uniquely specifies each different ALU operation. You also have a code to transfer the data of A and transfer the data of B, or just transfer the data of B. So ALU performs not only arithmetic and logical operation, it also performs the role of the multiplexer also, transferring. Now you have MUX LU. If 0 is selected, the data from this particular A is selected. If it is 1, the data from the line B leg is selected. So now, what is the data path for this? So you have, for the first step, time T1 from PC to MAR, we have the data path from PC. It is going to the mux. So it is going to be mux SA should be 1, and then this line should be selected. So arbitrarily, because it's B, so 0, 0, 1, 0, 1. If this is the code, it will just transfer the contents of B to the output. And then the line the contents is coming, the data from, if it is 1, the data from the B leg is selected and it is placed on the D bus, and the data is going on and it is given to MAR. Yes. Now here you also have PC in, PC out. So the data can come inside the PC or go outside the PC. You also have data can come inside the D2 register or go outside the D2 register. So D1, same thing, the data can come inside the D1 register and go in, out. The data can come from the instruction register and go outside the instruction register. So for the time T1, PC to MAR, what are the things it is going to be highlighted? PC out, the data is going out of the PC. Then multiplexer is selecting the value 1, so that the contents of the PC is transferred to the other line of it. And then this particular code should be generated so that it uniquely identifies the line from the B, the data, whatever is there, has to be just transferred to the output line. Then mux of LU of 1 should be selected, so that again the data will be transferred, whatever is there in the B line, without performing any operation. And then MAR in should be selected and out should be selected at the same point of time, while the data has to be placed on the address bus. So these are the control signal we will be generating. And finally, after a read operation, we can go ahead and create a data path for T2, T3, T4 in the same manner how we have created for PC to MAR. And after the instruction has come, the instruction register will send it to instruction decoder. And the instruction decoder will decode and it will generate the appropriate control signals. So now we will see, we will write for T1 how we are generating the control signals for PC to MAR. So you have instruction register in, instruction register out. You have PC in, PC out. You have MAR in, you have MAR out. Then you have D1 register in, out. You have D2 register in, out. You have IR is already there. That's MDRS D1 register. So then you have a multiplexer SA. It can be either be 0 or 1, so 1 bit is enough to represent. Same way you have mux NU, so it is 0 or 1, so 1 bit is enough. Then you have ALU, which has 5-bit code uniquely identified 1, 2, 3, 4, 5. So that each individual operation has to be performed. And then so everything has been clear. So to generate a control signal at time t1 from PC to MAR, PC, the data, the first step is PC, the data is going out. So that particular out will be highlighted as 1. Now multiplexer SA is selected only when it is 1. The data from the line B will be transferred onto the output of the mux. So in this case it is 1. Or else if you want to select the line 0, ALL, you need to write 0. So in this case it is 1. Then a 5-bit code has been selected. When this code is selected, the B leg, whatever the data is in residing over here, will be just be transferred without performing any ALU operation. So the code for the B leg to be selected, arbitrarily we have written 0, 0, 1, 0, 1. So we will write it 0, 0, 1, 0, 1. Then to select the data line from B, again MSLU should be selected as 1. Then MAR in and out, because the data is coming simultaneously and going out on address bus. Other things should be 0. So this is the control signal generated by the controller for when the contents of PC has to be transferred to MAR. As we told initially, the data movement, how the data moves, who will decide? The controller will decide. How will the controller decide? By generating the appropriate control signals. So like that we can write the code for T2, T3 and T4. We can keep on writing for a number of instructions. So having got this control word, so everything we are going to put into memory. So this entire control word will be residing where? In the memory. So consider this is the code for 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1. Like that you will be having, this is for T1. Like that you will be having for T2, T3, T4. For n number of instructions you will be having the control word. So the instruction decoder will select the appropriate or will point to the appropriate address. That address will be selected and that particular word, because we are selecting only one word. So because memory, we can say memory, as we told initially, memory we cannot store and retrieve one bit at a time. For that what we do? We go for 8 bits together, 16 bits, 32 bits to make up one word. So we will be accessing the memory in terms of word. So here we are selecting one word from a group of number of instructions and we will be placing. Because we are selecting one word, it is called as a micro word. So that particular signal will be generated. It is called as a micro word. So given a sequence, so T1, T2, T3, T4, this entire thing is called the micro routine. And we are selecting one word, it's called as a micro word. So like that we can generate control signals for T2, T3, T4, T5 and it goes on. So while talking about the data path, we have just discussed about PC to MAR. The same way, if you want to draw a data path from memory bus to D bus, how is the data path going to be? So from memory, it is going, and from here, this is the data path. For that, we can generate a control signal for type T3. And from D bus, again, this is the data path for type T4. Like that you can go on defining the data path, how the data moves from one place to another place inside a data path architecture and how you can generate the control signals. So with this we are very clear with a typical how the data moves from one place to another place and who controls it, how the control signals have been generated with the help of a control unit. Thank you.